Hi, my name is Rohit Sangaraju. I'm 17 years old, and my project is the Piezoelectric Vibration Sensing Shoe. Animals have inhabited our planet for many millions of years. The fact that they are still alive to this date proves that they were able to very effectively cope up with changing environments. My animal of interest during this project was the snake, drawing from my fascination with snake charmers and their ability to manipulate snakes with simple tunes. What was more fascinating to me, however, was the fact that snakes do not even have ears or internally contained eardrums. This made me wonder how snakes could hear and sense their environments. With the help of the internet, I was able to learn that snakes catch vibrations produced by moving objects or animals through their skin. Special nerves, known as mechanoreceptors, catch these vibratory signals, convert them into electrical impulses, and send them to the brain, where they are processed. In our world today, there are over 70 million deaf people and over 285 million who are visually impaired. Therefore, I decided to invent a technologically equivalent device which could mimic the biological concept of vibration-based environment sensing and help these people better navigate and avoid impending threats. After conducting some research, I was able to find a device known as a piezoelectric sensor. This device responds to any type of mechanical strain such as temperature changes, pressure, acceleration, and most importantly, vibrations. Therefore, I decided to incorporate a piezoelectric sensor acting as the technological equivalent of a mechanoreceptor. Drawing from the fact that a shoe is in consistent contact with the ground, my first design was to attach a piezoelectric sensor to the bottom of a shoe and use a microcontroller to read and process the signals. These signals would then be sent to a vibration motor, which could alert the user of the threat. However, before I began to work on my idea, I browsed the web to see if a device such as this was already invented. I found similar results, but nothing including the usage of piezoelectric materials. GPS navigation shoes. These are a good solution for those who are disabled and need assistance in traveling from one location to another. However, they don't fully protect the user from incoming threats, as their object detecting range is very small. Accordingly, these shoes require the user to have a smartphone with access to Bluetooth or Wi-Fi, making them very expensive. Close-range object detection shoes. This technology uses ultrasonic range-detecting sensors to detect objects in the proximity and warn the user. This is a creation inspired by the biological activities of echolocation and sonar sensing utilized by some animals. However, these shoes tend to be very heavy due to the many sensors mounted onto them and have a very small detection range of around 1 to 2 feet. After understanding that previous devices didn't have a large detection range and were more expensive, I went ahead with implementing my design into a prototype. This is a picture of the first prototype that I built. I attached the piezoelectric sensor to the bottom of the shoe so that it could be in contact with the ground and pick up signals. I mounted an Arduino Uno microcontroller and a breadboard with the main circuit on top of the shoe. For testing purposes, I simply taped 6 alkaline batteries to the side, supplying a total of 9 volts to the system. The vibration motor is hanging from the circuit and can be placed within the shoe or on the user's foot for alerting purposes. Although the sensor and the microcontroller were working well while stationary, there were some obstacles that had to be overcome before the project could be declared a success. First of all, the piezoelectric sensor's built-in detection range was only 2 to 3 meters, whereas I wanted to detect objects from at least 10 meters away. Therefore, I used the LM358 dual operational amplifier. This is a device which takes in a voltage and multiplies it by the amount of gain specified by the user through various resistor values. Using the general formula for voltage gain, I tested many resistor combinations and recorded them onto a chart. I finally chose two 22K ohm resistors as the secondary resistors and two 10K ohm resistors as the primary resistors in both amplifiers. The other values were either not sensitive enough or surpassed the Arduino serial monitor capacity. The second obstacle was that while walking, the shoe's accelerating motion will also be picked up by the piezo sensor and result in a false trigger. In order to avoid this, I split the signal on the circuit to read both the signal from the first amplification and the signal from the second. I used the first signal for cancelling out the acceleration movement and the second signal to actually detect vibrations. I specified my program to delay for 2 seconds while the reading from the first amplification was active. This way, while the shoe is in the air, the whole system freezes for 2 seconds and later resumes again, ready to pick up any vibrations. Overall, after overcoming these obstacles, my project definitely brought positive results and worked out as planned. I further tested on 3 different surfaces as outlined by this chart to see the responsiveness of the piezo sensor, and got the best results on the hardwood floor. These are a few images of my final prototype, which is extremely successful. Changes I made include the movement of the piezo sensor to the side of the shoe, and enhancing the battery holder.